All right, today we're opening up a case file on some pretty unusual suspects, rogue data points that we call outliers. Now, these little characters can lurk in our data, completely distorting our view of the world and leading us to all the wrong conclusions. So, you might want to grab your magnifying glass because our investigation starts right now.
It's a simple question, right? But the answer is actually pretty complex. See, a single data point, one that's way off from all the others, can tell a story that isn't true at all. It can mislead us, create these illusions, and completely hide what's really going on. So, how do we spot these lies?
Okay, take a look at this. This visualizes the problem perfectly. Graph A shows a pretty standard set of data, but watch what happens when we add just a few rogue observations, what the source material calls contamination. The whole picture just warps into something that looks like Graph B. It's the same reality underneath, but now it's telling a totally different story. A single point can really change everything.
To solve this mystery, every good detective needs to know their suspect, inside and out. So, let's build a profile. What exactly is an outlier?
Well, the classic definition from way back in 1969 gives us a great starting point. An outlier is just an observation that really stands out. It's the one that, when you look at the group, just doesn't seem to belong.
Then, about a decade later, Hawkins added this really crucial layer to it. An outlier is so different, it makes you wonder if it came from somewhere else entirely. It arouses suspicion. You start asking questions. Was it a mistake? Or is it telling us something totally new and important?
And these suspects, they have all sorts of origin stories. Some are just simple typos, a human error. Others come from, say, a faulty piece of equipment or maybe pulling data from the wrong place. But here's the kicker. Sometimes they're not errors at all. They are genuine, super rare events, a novelty in the data, that could turn out to be the most interesting clue you have. And that brings us right to the heart of the investigator's dilemma. What do? Do you throw out this extreme value and risk losing a vital piece of the puzzle? Or do you keep it and risk letting a single false lead poison your entire investigation?
To really understand the stakes here, let's visit a crime scene where these outliers can cause maximum damage. The world of economic inequality.
Now, what's really interesting is that in some cases, our suspect is, well, it's harmless. For example, when we're trying to measure poverty, the income of a billionaire doesn't really change the stats for people at the bottom. The outlier is basically irrelevant.
But the second we shift our focus from poverty to inequality, measuring the gap between the rich and everyone else, that harmless little data point suddenly becomes our prime suspect.
And all of a sudden, that same outlier is anything but harmless. The source material actually calls it a catastrophe. Why? Because inequality measures are designed to look at the entire picture, including those extreme values at the very top. Okay, so the technical reason for this catastrophe is a concept called the unbounded influence function. Yeah, I know, it sounds super complicated, but the core idea behind it is actually pretty simple and incredibly powerful.
So in plain English, unbounded influence just means that a single extreme data point acts like a supermagnet. There's no limit to its pulling power. It can literally drag the entire result so far off course that the final number doesn't reflect the reality for almost anybody else in the dataset.
Let's make this real. The Gini index is a super common tool for measuring inequality. When you calculate it on one particular dataset, it spits out a result of 84%, which is a shocking level of inequality. But is that the whole story? Well, watch what happens next. After a process called iterative trimming, where we carefully deal with just a few of the most extreme values, the Gini index plummets all the way down to 68%. The story of inequality in this society just completely changed, and it was all because of a handful of outliers.
So, if these outliers are so powerful, how in the world do we find them? It's time to open up the Data Detective's Toolkit and look at the methods for tracking them down.
The very first step, always, is to get your eyes on the evidence. Detectives graph the data. A plot like this one gives you an immediate feel for the shape of your data, where things are clustered and any points that just seem a little off. Then, we bring in the specialist tools. A box plot, like this one, is designed specifically to flag suspicious points. You can see the main cluster of data right there in the box, and then way up top are our suspects, clearly separated from everybody else.
Now, beyond just visuals, we have statistical tools. The source highlights two approaches. There's the simple way, which is a quick fix, but honestly, it can be easily fooled. Then you've got the robust way. This one's smarter. It uses measures like the median instead of the average that are naturally resistant to being pulled around by those extreme values. It's kind of like having a tool that's designed to ignore the loud noise and just focus on the real signal.
All right, we've identified our suspects. Now for the final act. What do we do with them? Let's see how the data detectives close the case.
So what's the move? It's not as simple as just deleting the data point. There are three main strategies. First, we can reduce its weight, which means we let the outlier stay, but we basically tell our analysis not to listen to it as much. Second, we can change its value with methods like trimming, where we gently nudge that extreme value closer to its neighbors. And third, we can use robust methods from the very beginning, techniques that are built to be skeptical of extreme data in the first place.
But here's the final, and maybe the most crucial clue of all. We have to remember to be gentle. An outlier might not be a mistake. It could be a real, genuine, maybe even a groundbreaking discovery. And that's why documenting every single step and just thinking critically is so important.
And this brings us right back to why we need those smarter, more robust tools. The source material warns against these overly simple strategies. Quick fixes often assume that your data looks like a perfect, symmetrical bell curve. But real-world data, like income or spending, it's rarely that neat. It's usually messy and skewed, and our methods have to be smart enough to handle that reality.
So, the next time you see a statistic or a graph, you'll know the secret of the outlier. You can start asking the right questions, looking for those hidden clues. You're the detective now. So what story is the data really trying to tell you?